Thank you. So my name is Arseniy Revchov, and today I will present my research of random number generators that I conducted back in October 2017 to find vulnerabilities and flaws in smart contracts in the Ethereum blockchain. So before we start, a few words about me. I work for Positive.com. We do smart contract audits. Also, we protect ICOs. I'm also the team member of PhD Security Conference. And by the way, the CFP is open. And I'm also a web security blogger. Check out my blog at razor.name. So my presentation will be divided into the following parts. Firstly, I will talk about the blockchain itself, the Ethereum and smart contracts, because this is not a blockchain conference. Then I will move to my actual research about the results. Then I will talk about how to implement a safer random number generator in smart contract for a smart contract in the Ethereum blockchain, and then some results of my attempt to automate the discovery of such vulnerable contracts. And there will be one more thing at the end. There will be a contest for you to try your skill at hacking such contracts with vulnerable random number generators, and you will have a chance to win some prizes. Okay, let's start. So the first part is about blockchain principles, Ethereum and smart contracts. So I think that most of you know what blockchain is. It's basically, like the name implies, is a chain of blocks. So each block has a hash of a previous block, and it allows to have the chain of all the data that is stored in these blocks. And this data is are transactions, like transfers, some for Ethereum, for example, it may be code execution and so on. That is why blockchain is incorruptible. You cannot reverse its state. It always moves only forward. It is also transparent. It means that you can see all the transactions in each block. And it is also decentralized. It means that if a single node in the blockchain network goes down, then it won't make the whole network unavailable. There were two stages of blockchain development. The first stage was the appearance of Bitcoin, the so-called blockchain 1.0, and Bitcoin forks like Litecoin and others. And more recently, a new blockchain technology, so-called blockchain 2.0 has appeared with the Ethereum and its ability to run smart contracts. So what is Ethereum? It is basically a distributed world supercomputer, according to the words of Ethereum founders. So there is a language, a high-level language like Solidity or Serpent or Aper. The most popular one is Solidity. And you can write smart contracts with it. Smart contracts are basically just a program, and Ethereum runs these programs on every node in its network. This high-level language is then is transferred to bytecode, and this bytecode is run in EVM, Ethereum Virtual Machine. And each client has an instance of this virtual machine. There are two types of accounts in Ethereum blockchain. The first one is called externally owned accounts. These accounts are just regular accounts like in Bitcoin. So they have Ether balance, they can send transactions, and they are controlled by private keys. Unlike regular accounts, contract accounts have associated code, which is basically bytecode that I mentioned. Contract accounts also have Ether balance, and they can execute code when you, for example, send a special transaction. And this code is Turing complete. It means that you can compute literally anything in EVM. And of course, it opens doors for hackers and for bugs and vulnerabilities in these smart contracts. Solidity is the most popular language to write smart contracts. It looks like JavaScript, but it is strongly typed. It has no string operations, it has no floats, and it is mainly used to run ISOs and to make ERC20 compatible tokens. And Solidity is Turing complete, as I said. So Solidity smart contracts have bugs, and especially in lotteries and card games, because they have random number generators that I found to be vulnerable. So the next part is my actual research of the random number generators in Ethereum blockchain. So what I did, I basically grabbed all the smart contracts on etherscan.io and also looked for interesting contracts in GitHub. I used Elasticsearch. This is a database that has also a nice UI called Kibana. And using this user interface, and Elasticsearch capability to search contracts, not just contracts, but any text, I found 72 unique implementations of random number generators that can be found in the wild. And out of these 72 contracts, 43 were vulnerable. I don't claim that this research is complete. It was done in October of last year, and it was done manually. So there may be some more, of course, contracts that may be vulnerable. So I have discovered that there are 4 categories of such vulnerable contracts. The first one is based on block variables, also on passblock hash, and private seed, and those that are prone to front running. I will explain each of these categories later. So let's start with random number generators that are based on block variables. I have found that there is a certain number of contracts that misused block variables to provide random numbers. EVM provides several block variables that can be wrongly used in contracts as a source of entropy. For example, Coinbase, which is the address of the miner who have calculated the right hash for the block. The difficulty is a measure of how difficult it was to mine this new block, just a number. Gas limit, it's a specific term for Ethereum, which means the limit of gas consumption of all transactions in the block. Gas is a measure of like in real life, in order to run to drive a car, you need gas, and to run smart contracts, you also need some some gas, which is a measurement of operations that can be run in EVM. Each operation has a certain number, a certain cost to run on in EVM. EVM, for example, to store some value, you must pay lots of gas, for example, and just for example log a message, you need to pay a small amount of gas. So it may be weird, but yeah. So this gas limit just also a number that in some contracts is deemed unpredictable, but it's not. Also the number of the block and timestamp. I think it's you can understand what it means. So why RNGs that are based on block variables are vulnerable? Actually, you even don't need to be a miner to be able to predict the outcome. In Ethereum, you can make an exploit contract that will just issue a so-called internal message. So it will call the target contract, and the state of RNG will be the same, because if it relies on block variables, the value of these variables will be the same both in exploit contract and in the target contract. So these are examples of simple RNGs that are based on block variables. So as you see, this RNG just relies on block number, and of course it can be considered as safe, and the author admits that in a comment. Another example, in this example you can see that timestamp is used as a source of entropy, and of course it cannot be secure. In this example, the contract uses Coinbase, the address of the miner, and the block difficulty variable. And of course, if you call the target contract and use the same code in your exploit, the outcome will be the same. The second category of vulnerable generators is those that are based on block hash. Block hash is a function in EVM that allows you to get the hash of a specified block. And there are three common major variations, vulnerable variations of misused block hash function. So the first variation is just getting the block hash of the current block. The second one is the block hash of the last block, and the third variation is getting the block hash of some null block. So let's start with the first one, the block hash of the current block. What's wrong with this approach? You need to understand that when you execute the code, like on the screenshot, the block number will point to the actual number that is incremented each time a miner picks up new transactions and creates a new block. So at block initialization, the block number is known, so EVM will provide it. However, the block hash of the current block number is not known because the miner has not yet calculated the hash. That is why the block hash of the current block number will always result in 0. It's obvious. But as I discovered, there are many contracts that think that the block hash of the current block number will actually result in a hash. For example, like this contract, you see that it uses block hash of the current block number for some card game. Or like in this example, I have submitted an issue to GitHub. It's ExomZen project. ExomZen is a developer of CryptoKitties, if you know, which was very popular. It was actually hype about 2 months ago. The second category is block hash of the last block. The principle of the attack is the same as the block hash, as the RNG that is based on block variables, because again, you can create an exploit contract, just copy the RNG code and call the target contract, and the result of the RNG in your contract and the target contract will be the same. This is one example of such contract. You see that it just tries to get the block hash of the last block. And the third category is the block hash of a null block. There is a peculiarity in EVM that it doesn't allow to get all the block hashes. There is a limitation of 256 blocks, and Solidity documentation warns about it. However, many contracts tend to just ignore, or I don't know, just didn't see this warning, but it's a fact that they don't check that block hash of a null block actually gives some meaningful example. But if you try to get a block hash of some older block, you will get again 0, which makes it predictable. This is the case of Smart Billions lottery hack. The lottery used a block number when the bet was made and put it in its storage. When the user requested the lottery to announce the winning number, the smart contract just retrieved the saved block number and tried to calculate, not calculate, but get the block hash of that block from EVM. But it failed to validate that the hash is actually a hash. So it didn't validate the block number H. And there was actually a bug bounty organized by the owners of this contract, and they asked everybody to look for vulnerabilities in their code. They were so sure about it. However, in 2 days, some guy found that it didn't correctly validate this block number H, and he managed to steal 400 Ethereum from this contract. But the developers of this lottery decided that they will stop this and withdraw all the remaining funds. So they were cheating, actually. And the last category that is associated with block hash is variation with a private seed. Um, in its nature, blockchain is transparent. It means that, as I said, uh, you can see any transaction, see every operation that was done, and you can see also the internal storage of each contract. There is in Solidity there is a private scope that limits that restricts other contracts from accessing your storage, the storage of your contract. However, you can fetch any storage item off-chain. It means that you can see all the items using, for example, a popular Ethereum client called Web3. One of the most interesting examples of such vulnerable random number generator is the Ethereum lottery that I found firstly on GitHub. So this is the extract, a fragment of its random number generator. As you see, it tries to get the block hash of a block number with some offset pointer. And this pointer was defined as a private, with a private scope. So the author thought that nobody would get the value of this pointer. Nobody would be able to get this right offset to be able to get the block hash and calculate the random number. However, when I reported this issue to the author, he actually was sure that there was no mistake from his side, and he asked me to prove it if it's really vulnerable. So challenge accepted, and using this exploit, which basically used the same random number generator as a install Ethereum contract, and using a pointer that I obtained off-chain using Web3 Ethereum client, I was able to snatch all the Ethereum that was on this contract. Actually, there were some more comments from his side. He still didn't. He said good job, but he still failed to implement a proper random number generator. So be sure to check out the GitHub link. It's funny. So the fourth category is called front running. To understand front running, you should get some understanding of how transactions are put in a block by miners. So in practice, miners want to get the maximum reward for their calculations. So they pick up the transactions based on the total consumed gas. The gas, as I explained, is measurement of how difficult it was for a node, for Ethereum node, to run your smart contract. So they pick up only large transactions, and they order them in each block by the gas price. So if you set a larger gas price, so your transaction will be the first in the block. And the order of transactions in the block is quite important, because if the contract execution depends on its position in the block, then it may pose a security threat for such contract. An attacker just may watch the pool of pending transactions, and he may watch for externally submitted random numbers and issue his transaction that will be the first, that will be prior to this transaction with a random number, and it makes it vulnerable because the EVM will execute the attacker's transactions first, and he will guess the number before it was announced. This was the case at the contest organized by Zero Nights conference. There was a smart contract and a robot which submitted random numbers at some period of time, like one number in a minute, and the task was to guess the number. Of course, it was vulnerable. Using front running, you could just observe all the transactions in pending transaction pool and issue your transaction with a high gas price, so that your transaction will be executed before the robots one. So it effectively made you the winner of this lottery. And another example is the game which I found on the blockchain called Last is Me. The logic is simple. Every time a player buys a ticket, he claims the last seat in the round, and the timer started the countdown. If nobody claimed the seat within a certain number of blocks, then the last player wins the jackpot. So again, this implementation is also vulnerable to front-running issue, because you can again observe pending transaction pool and watch for other contestants' transactions and claim the jackpot with a transaction with a high gas price. So this was the part about vulnerable random number generators, and the next one is about how to build a safer one. There are three main implementations that can be used as a safer approach for random number generators. The first one is using external oracles. Blockchain is deterministic. It means that it cannot access the environment, its environment. So in order to, for example, fetch currency rates or weather or something else, you need to use external oracles. This is the scheme of how such oracle may work. The most used service is called Oraclize. It allows a smart contract to get the result or get any page from the internet. And I found that many contracts use Oraclize to request random.org website, which is a source of random numbers for public. But in this case, several questions arise. Can we trust Oraclize? Because as you see on the scheme, there is an Oraclize service running on a box at Amazon, for example. and we cannot be sure that it's not tampered. We cannot be also sure about random.org and all the underlying infrastructure, because anything can happen, and it can be theoretically also tampered. OracleIce provides some means to verify the results. For example, TLS notary. But it can be verified only off-chain. It means that you cannot check that the results were indeed correct in your smart contract in the runtime. You can do it just afterwards when the, for example, winner was determined. OracleIce provides some even better means using ledger proofs, and it allows to verify the results on chain. These are some examples of the lotteries that use OracleIce. Another external oracle is BTC Relay. BTC Relay is a bridge between Ethereum and Bitcoin blockchains. And I found an example of a smart contract that uses future blocks of Bitcoin as a source of entropy for Ethereum smart contract. But again, the means of protection in this case is the sole fact that Bitcoin price is higher than Ethereum's, and miners won't be cheating in this example. But we can be sure that they won't be cheating. It's just about the price of Bitcoin. So it just makes it harder, but does not eliminate the possibility entirely. Another approach is called Signergize. Signergize is suitable for contracts where there are two parties, the player and the house. It uses cryptographic signature as a source of entropy. And the procedure is as follows. Firstly, player makes a bet by calling smart contract. The house, the smart contract, sees this bet, then signs it with its private key and sends the signature to smart contract. Then smart contract verifies that it is correct using non-public key. And then the signature is used as a source of entropy. It is used to generate random numbers. So what is wrong with this approach? It can be also misused because the only built-in means of cryptographic signature in Ethereum is elliptic curve, ECGSA. And this algorithm allows the house to cheat, because in ECGSA you can submit a parameter k. You can choose the k so that the output signature will benefit the house. And this is the problem, because the house can cheat. And you can see an example of such implementation on the link. I will also share my slides afterwards. The correct approach is using RSA-based signatures, because in RSA you cannot manipulate input parameters. There is no such key, and RSA is safe against this type of check. And thanks to Metropolis hard fork of the Ethereum, modular exponentiation operation became available, so anybody can implement this algorithm in their smart contracts. And there are some open source implementations of RSA for Ethereum. And the last approach that you can use to make safer random number generators is a commit reveal approach. Commit reveal is two-phase. I want to say that any implementation that determines the winner in just one transaction is always vulnerable. To make it safer, you need to use at least two transactions. In the first transaction, the so-called commit stage, the owner submits a hashed seed, no clear text. Then the smart contract saves this hashed seed, and in the second stage, called reveal, the owner announces clear text seed, and smart contract verifies that the hash of the seed in the commit stage is equal. So it just checks that the seeds are correct using the hash that was submitted earlier. In commit reveal, a proper commit reveal should rely on multiple patches, because when there is a single patch, for example, when only owner submits his hash seed, there is a problem, because the owner can also be the player, and when he knows the original clear text seed, of course he can choose the right time, and he can know the random number beforehand. These are some examples of commit reveal with float single party approach. A better commit reveal implementation is RanGeo. RanGeo is a RNG that collects hashed seeds from multiple patches. So literally anybody can participate in each iteration, and he can submit his hash seed, and then each party is paid a reward for his participation. And this approach is good in for the reason that nobody knows each other's seeds, and the result can be considered as truly random. However, if a single party refuses to reveal the original seed, it will result in denial of service. I think the best implementation of commit reveal and best implementation of random number generator is a commit reveal with a future block hash. So there are three sources of entropy in this case. First one is the owner's hash seed, the second one is the player's hash seed, and the third is a future block hash that is not known to anybody beforehand. So the random number is then generated as a hash of two seeds and a block hash. Check out the link below, which explains in detail how this implementation works. It's good because it solves miner incentive problem. So miner can decide on block hash, but he doesn't know the owners and player seeds. It also solves owner's incentive problem because owner doesn't know the future block hash, and it also solves the case when the player is also an owner and also a miner. It's of course unlikely, but this approach solves even this case, because no, the person doesn't know the block hash. He doesn't know the owner's seed and doesn't know player's seed. And the last section of my presentation is about the attempt to automate the discovery of such vulnerable implementations. There is a tool called Mithril, created by Bernard Miller, which allows to scan Ethereum for vulnerabilities, to find vulnerable smart contracts. It uses a symbolic execution engine called Z3, which allows to construct the call graph of a smart contract. And having this call graph, it is possible to find the, for example, asset transfers that are constrained by, for example, block variables. So I decided to use this platform to make a plugin called VicRandom that allows to detect such unsafe value transfers that are constrained by predictable block variables and pass block hashes. So that's it. Thank you.
If you have any questions, raise your hand and I'll bring the mic to you.
Thank you. Thank you very much for the interesting talk. One question for you, a little speculative, if you will. Do you think the prevalence of some of these poor implementations is frankly laziness, or is it maybe indicative of some folks trying to game the system for their own benefit, you know, criminals or Hacker Underground, et cetera? And yeah, just kind of curious on your thoughts about that.
Well, I think that the main reason of these vulnerabilities, I think that it is maybe ignorance or just the technology that is too new for developers. They didn't catch all the new things, because blockchain is very different. I saw many examples when web developers try to make such games, and they don't understand the concepts behind blockchain. And of course, it leads to vulnerabilities. So they do not understand the platform in the first place. And I think that it is the main reason. I can compare it to web security when back in 2000, maybe 2005, when PHP was popular. Many people got into web development and they did all it wrong. And the language PHP favored such bad practices. It didn't restrict proper usage. And I think that Solidity, the main language for writing smart contracts, also does not provide solid means for safer programming. So that's it.
Yeah, hi. So you brought up the fact that a lot of developers don't understand the blockchain and the technology very well. I'd have to agree with you, which is why, for example, personally, when it comes to Bitcoin at least, there is a really good book by a gentleman named Andreas Antonopoulos. He's kind of famous in the scene, and he wrote the Bitcoin book, which it's a book built for programmers to understand all the different facets of blocks mining the peer-to-peer network of Bitcoin, and I think they're working on one for Ethereum right now. But I feel like when one tries to learn about Ethereum and smart contracts in particular, it's really its own thing. And where are those good resources where you can go from a bottom-up kind of approach and learn the nitty-gritty details? Because I feel like as a developer, when you know the details of it, then as you're writing that code for the random number generator, you would be able to tell, oh yeah, this seed, can be, discovered, by, using that W3 service. So like what resources would you recommend? Because I'm sure there's maybe other areas of smart contracts that are highly vulnerable, that are not random number generators and could be exploited just as easily within the coming months or even years.
The resources is also a great problem because I think that there is a lack of such resources, of such guidelines. I can recommend security best practices for Ethereum smart contracts by consensus. It has really good recommendations for better programming. But as for random number generators, you should just make your own research before going into it, because there is no common pattern, no common library for it. So to understand it, you just need to open the debugger and test things. You cannot just blindly think that, okay, I think that the result of, for example, this block hash will be my actual hash. But as you see, it will be 0 in some cases. And even the official documentation also lacks some important notices, and much work should be done in this direction to improve the basis for safer programming in Ethereum.
Just a follow-up on that. You mentioned that when the hash ends up being 0, I kind of missed that part in your presentation. The example was that the developers, or in that case, are using the hash for the next block, and that ends up being 0 sometimes. So how's that?
Yeah, they use of the past block. This is the problem. The correct approach is to use the hash of some future block, but for some reason they think that the hash of the past block can be used as a source of entropy, which is not true, of course.
And that's because the previous block is known, right? The hash
Yeah, of course, it's known.
So then what is then when in that example where you showed the on Etherscan that it was 0, how is that even possible?
It was the example of current block when the block hash of the block number was calculated. So not the past block, not the future block, but the current block, and the block hash of the current block is 0.
Okay.
Thanks for the talk. That was a lot of information. And another question is how is the future blocks hashes calculated if you don't have the transactions yet?
Yeah, to know the block hash of a future block, you need a second transaction. As I said, any implementation relying on a single transaction is flawed. So you firstly need to store the block number, and then you need a second transaction to retrieve the block hash for that block number. And that block number will point to a block that was unknown at the time when the first original transaction was made.
Okay, so you mean it's just a hash of the next or whatever the next block numbers, but not the entire hash of the two transactions and all the
Yeah,
things?
just of
The block number.
Yeah, the block number of the block when the bet was made.
Yes. Okay.
Of
thank you.
the first stage.
Hi. So what are your thoughts on formal verification? Can you use formal verification on the smart contracts, and will it be able to, for example, catch these kind of bugs?
Well, I think that formal verification is actually a good approach, and I think that such bugs can be formally verified, such cases. And there is an attempt by Bernard Mueller that I mentioned previously to perform formal verification for some vulnerabilities, and you can check out the blog post that he recently made about it. And there is also an attempt to formally verify ERC20 tokens using the K language. And as I know, there is a working proof of concept as for now. So I think that, yeah, formal verification is a proper solution for eliminating such bugs.
Any other questions? Okay, thank you.
So thank you, guys. Also, there is a contest that I mentioned that you can participate in and win the Ledger Nano S. This contest features the examples that I showed in this presentation. So if you feel confident and lucky, you can try your skill. Thanks.